All right, some quick reminders of things we're going to use during this particular lecture on 4.2 area. The summation formula for I squared from I is equal to 1 to n is this particular formula. And then limits at infinity. So that we addressed this last time when we looked at horizontal asymptotes. But the main idea is if you have the largest exponent, see these ones are smaller, if the largest exponent agrees in both the numerator and the denominator, then you look at the coefficients for the limits at infinity. So this particular limit at infinity would be 6/8 or 3/4. Let's talk about area underneath the curve. So if we have a function y equals f of x, and we have a upper and lower bound of lower bound A and upper bound B, then we can approximate this area by dividing it into rectangles. If we're looking at what's called upper sum rectangles, we pick the y value on the right-hand side. So again, B has two sides. One is smaller than the other one. The one on the right-hand side is the larger x value. So this is known as the upper sum. Whether it's an inscribed rectangle that lies inside the curve or a circumscribed rectangle that lays above the curve actually depends on whether it's increasing or decreasing function. All right. So again, basic concept, if we have two rectangles and we're looking for upper sums, we pick the larger x value of the two. So the larger x value of this rectangle is this guy. Here's the y value for the height. And on the left-hand rectangle, this guy here's the height. So we just draw straight over to the other rectangle. All right. So these two rectangles, if we added their area together, it would be approximation of the area underneath the curve. Each has width of b minus a over 2. This is known as delta x. Okay, if by some chance we split it into 4 rectangles and we were looking for a lower sum, then again, now let's take a look. Here's the first rectangle, its lower x value is up here, so that would determine the height. The second rectangle, its lower x value is to the left, so this determines the height. The third rectangle, height is determined here, and the fourth rectangle, the last rectangle, the height is determined by the left-hand side. These would become lower sums, even though they are circumscribed rectangles and are above. That just happens because it happens to be a decreasing function. All right, and again, let's talk about this delta x thing. This length of the interval, b minus a, over the number of rectangles gives us something called delta x, which is going to be the width of each of these particular rectangles. It is also going to be the basis of the substitution when we start putting it into the formulas like this that we talked about before. Okay, let's look at a couple examples. We're going to do one with a finite number of rectangles. In this particular case, we're going to do rectangles is equal to 4 again. So looking at the function y equals 2x squared, bound by the x value 0, 1, and the x-axis. Most of these are going to be between the graph and the x-axis. So what I'm looking for is the area underneath this curve. This approximation is going to be too big because as I used upper sum rectangles, they're all going to be determined by the higher of the two values, right-hand side rectangle, right-hand side rectangle, right-hand side rectangle, and right-hand side rectangle. However, it's still going to be an approximation. So what do? We take 1 minus 0 over 4. This is delta x. The length of this interval, again, is 1 divided by the number of rectangles 4. This is delta x. So here we go. 1/4 times, and then I just plug the right-hand side in here. This is 1/4 squared times 2. This would be the height. If I looked at the next one, this would be 2/4 squared times 2. This would be the height of this next one. Okay. If I looked at the next one, this would be 3/4, and the height would be 3/4 squared times 2. Okay, I got to plug it into the original function to get the y value, and so forth and so on. 2 times 4/4 squared times 2. So what do? We can rewrite. We can pull out the 1/4, which stands for the width of each of these. We can pull out the 2 that simply came from the formula, and what we're left with is 1/4 squared plus 2/4 squared plus 3/4 squared plus 4/4 squared. Now understand this. All of these denominators, if I square them, would all be 16, so I can pull out this 1/16. This 1/4 and this 2 just became a half. I pulled out all those denominators as 1/16, and what am I left with? The interval, the summation of 1 to 4 of I squared. If you'll notice, this would be 1 squared, 2 squared, 3 squared, 4 squared. So I can just write it that way. All right, so I go ahead and put in the formula. This is the formula we talked about doing before. I multiplied these two together, 1 over 32 times, and then this would be n times n plus 1 times 2n plus 1 all over 6. A little bit of simplification here winds up with 15/16 as our area. This is too big. We talked about the fact that these rectangles are all above, but it still is an approximation of area. All right, so if we wanted to make it an exact area, how would we do that? Well, we let the number of rectangles approach infinity. So again, we still got the bounds, lower and upper bounds from 0 to 1, so 1 minus 0 over n, because n is the number of rectangles this time, and this is going to be delta x. So now we're going to write this as a summation formula. 1 over n, again, this is width, times, and then these are all just the right-hand intervals. This is just the upper sum. 1 over n squared times 2 represents the height of the first interval. 2 over n squared times 2 represents the height of the second interval. 3 over n squared, 4 over n, all the way until we get n over n squared, which of course is just 1 squared times 2. This would be the height of the very next rectangle. Okay, so how do I rewrite that? Let's take a look. I take this first 1 over n out, and then I see what's left. All right, there's a 2 that's left, and I actually should have taken that out to begin with, so I went ahead and put the 2 out there first. This is the 2 over n, and I've got I squared over n squared, basically, once I square this. So the 1 over n squared comes outside, and the I squared stays in. So outside, I'm left with 2 over n cubed, and inside, I look at the formula, n times n plus 1 times 2n plus 1 all over 6. So again, let's take a look at just the highest exponent. N times 2n is so far 2n cubed, times 4 is 4n cubed. There's a bunch of junk after that, but I ain't sweating it. Down here, the biggest exponent is 6n cubed. So basically, I got 4n cubed over 6n cubed. It goes to the coefficient. So this area is actually 2/3, and this is exact. All right, we'll do a few more of these, but I'm going to go ahead and just show you the homework for a few minutes. And maybe I'll go over 47 since we're here. This said the function is y equals negative 2x plus 3, and let's subintervals equal n. So if we take a look at the actually, let me show you that I did this beforehand. So if we're going negative 2x plus 3 from 0 to 1, literally that's a trapezoid. It has a base here, a height of 1, and this base is 1 and this base is 3. So if I have a heights and two bases, then this is 1/2 heights times base 1 plus base 2. Therefore, the area here of this thing is 2. This is just using geometry. I'm going to show it to you also with the subintervals that we just talked about. So again, since we're from 0 to 1, we do 1 minus 0 over the number of rectangles. This is delta x. So now we start plugging it in then. So if we're looking for this, then we're plugging it into the bit here. 1 over n times, and then we look at the height on the inside. If we take a look and we start substituting over here, this is 1 over n, negative 2 times 1 over n plus 3, negative 2 times 2 over n plus 3, negative, in general, negative 2 times I over n plus 3. This 1 over n here is the width. This is the basis of substitution in here, very similar to the other one, and then I just start factoring stuff out. I can take the negative 2 over n out, and then I'm left with 1 over n times negative 2 over n, and then this is summation of I plus 1 over n summation of 3. And I'm just kind of breaking some of these summations down. All right, when you break them down and put them in your formulas, again, I ignore the rest. I get negative 2n squared over 2n squared, and I get 3n over n. This is negative 1 plus 3, which again says our area is 2. Same thing that we got before. All right, we'll hit more of them in class. Thanks.